Hello guys, in this video I would like to discuss about MYP chemistry. So the chapter is understanding matter. So when we hear the word matter, usually it's something that takes up space and also has mass. Yeah, most of the time in this level we are going to speak mostly on physical matter. So don't think about any other form of matter. And usually this matter would be differentiated into three states. So the first one is solid, liquid, and gas. We're actually classifying the states of matter based on the arrangement of the atoms. So if we are able to zoom in very deeply into the atoms of a certain thing, then we would be able to see this visualization. So for solid things that we see, the atom arrangement is very tidy. So they are packed. And then it's kind of not moving, but it's actually vibrating. So they are doing vibrating. So they are vibrating in place, in position. So they're really not moving around, but they are still vibrating in place. And also like the gaps, it's very tight, very packed, very tidy. The arrangement is very regular. While for liquid, so the atom arrangement, some of them are still touching each other. However, it's like a little bit loose. And the atoms are actually able to move, so they can move and slide past each other. For gas, you see that the atoms are far apart, and that the atoms, they are free to move, and they move very quickly in all directions. So no specific directions, they just move all over. So matter can actually change states. And how can they change states? In our universe, if we want to change something, then we need energy. If we want to transform something, we need energy. And in this case, one of the easiest source of energy that we can give to these atoms is heat. So heat is actually relatable to temperature. So by increasing the temperature, usually it's often associated that we give heat to the system. So if we give heat to the system, we have something called kinetic theory. By providing heat, actually the atoms will gain kinetic energy. So they will move even more violently. For example, here in solid atoms, if we provide heat, then they will actually vibrate more violently, and then they will become less structured. Because they vibrate, so they will try to break out of this structure. In this case, solid things can actually melt to become liquid. And if we give even more heat to liquid, then they will try to break free. The atoms will try to break free of this structure, and then they will move quickly in all directions. So liquid to gas, they are doing boiling or evaporation. So by providing heat, then we see that the atoms will move more significantly. The atoms gain kinetic energy to break the structure. While if we lower the temperature, actually the atoms will lose kinetic energy. So they will become closer. They will become even more packed. There is a term that I need to explain to you. The term is called intermolecular forces. So for example, we have a glass of water here, a glass of water. Of course, if we zoom in, a glass of water will not be composed of only one water molecule, right? So there will be like multiple billions, trillions of water molecules. There will be something like this. And between these water molecules, actually, there is an invisible force, attracting force, that's keeping them together. So something like this. So imagine like it's a glue that connects them so that when they move as if they're one unit. They're flowing as one unit. It's called the IMF, or the intermolecular forces. So when we give kinetic energy, when we provide heat, actually the atoms will move even more violently. So in the end, what is originally something like this, so the atoms will be more free to move to all directions. Meaning that here, in the gas state, that the IMF, the invisible attracting forces, they're more or less being broken. So what kinetic theory explains, actually when we provide heat, we provide energy, the atoms will move. Eventually they will break the intermolecular forces. They're trying to break free, they're trying to move, they want to be free. But when we reduce the temperature, we're taking out the energy, the atoms gets closer and closer, they will form attracting forces because they're already close. So transformation from left to right, you see, from solid liquid, then liquid to gas, we're actually breaking intermolecular forces. The atoms are breaking the structure, while transformation from right to left, you see gas to liquid, usually it's called condensation. And liquid to solid, freezing. So they are forming new intermolecular forces, forming new attraction forces, so they get closer and they become more tighty, they become more packed. In some rare occasions, solid can bypass this process to become gas immediately in a process called sublimation, while gas can also be solid immediately in a process called deposition. Okay, so regarding movement of atoms, we have one more thing to discuss, which is diffusion. So diffusion is actually movement of atoms from high concentration, so high concentration to low concentration. So imagine that you have like a water here and then you put some coloring agents here, Well, initially that the pigment concentration will be high there. However, this thing will slowly diffuse, yeah. So this thing will be kind of purple. This will be not too purple, a bit purple, something like this. Until eventually all of these things will be of the same color. So the atoms are actually moving, they are free to move, they're bumping each other randomly until all of the water would be having the same concentration. So just like, for example, you dissolve salt here, salt in a water, then eventually after some time the atoms are actually moving, right? The atoms are not silent, they are not stationary, so the atoms will move, bump against the salt particles, and then finally distribute the salt particles across the water evenly. So this is called diffusion. And there are some things that can affect diffusion. So first is actually temperature. So if we increase the temperature, we give kinetic energy to the atoms. Means that they can travel faster, they can bump each other more often, so they can carry the particles evenly quicker. And the second is actually the concentration. So the higher the concentration of something that we put, well, the diffusion rate will be even more quick, right? So high concentration to low concentration. So the more extreme we make the difference, the more diffusion we will see. And also mass particles, so the mass of the particles. So if the particles is actually heavier, then they will move slower. So lighter will become quicker. Lighter things will diffuse quicker compared to heavier things. So these are all about state of matters. So now we would like to move to fundamental subatomic particles, which are electron, proton, and neutron, and atom particles. So we would like to see the atoms in depth. So atoms are composed of some subatomic particles, meaning subatomic means that they are within the atom, smaller than an atom. So we have electron, which is negatively charged, proton, which is positively charged, and a neutron, which is neutral, so they don't have charge. Neutron and proton would actually be located in the center of an atom, which is called the nucleus. while the electrons will be orbiting the atoms in what we call shells. So proton, neutron, and electron, they have distinct properties. So about the charge of electron will be -1, the charge of proton will be +1, and the charge of neutron will be 0 because it's neutral. And the relative mass, so the mass of electron would actually be negligible. So in most of the time, we would actually ignore the mass of electron, while the mass of proton would actually be 1 and the mass of neutron will be 1. Is this 1 kilogram? No. So this is actually 1 unit. 1 atomic mass unit. 1 unit or just 1. Sometimes we also omit the unit. So it's 1. Technically, this is relative. So that the mass of proton and neutron more or less is the same. So that's what it's saying, relative mass. While electron is so light. So imagine that this is a person and he's wearing glasses. So when he's going to take his weight on a scale, I don't think he needs to take off the glasses, no? Because the glasses is so light compared to his body weight. So that's why we can actually kinda ignore the weight of the glasses. So it's kinda the same thing, that the mass of an atom is mostly composed of proton and neutron. So this composes the mass of an atom. While the electron, the mass we can kinda ignore. So if we see a periodic table, so for example, we have sodium, there would be some numbers. So the numbers on top would be what we call atomic number. So atomic number provides information about the number of proton. So we have 11. And also electron. We also have 11. Well, this thing here, we have what is called by mass number. Well, the mass is actually composed of proton and neutron, right? So this is actually proton and neutron. So since we know that the proton is 11, so we can actually deduce the number of neutron. So in this case, 23 is equals 11 plus neutron. So the neutron would be 12. So the mass number would always be a combination of proton and neutron. While the smaller number generally would give us information about the number of proton and electron. Usually they are the same. Because they are the same, so the charge, the positive charge and the negative charge, they are cancelling each other. This is why in regular atom, they don't have charge. So they are kind of neutral in charge. While neutron, they don't have charge. So if we see that now sodium has 11 electrons. So we can imagine that the structure of sodium, Na, 11 protons would be in the middle. 12 neutrons will be in the middle as well, while the 11 electrons will be distributed evenly throughout the shells. So they will be distributed throughout the shells. So how can it be distributed? So of course it's not random. There are some rules to follow. So imagine that we have a lot of balls here. We have a lot of balls, and then you're trying to tidy up your toys and then try to put them in boxes here. So we have box, and etc. So of course we will try to put, you will try to put these balls in the box that is closest to you first, because it requires the least amount of energy, right? And then after this is full, then you move to the second box, third box, and etc. So the first box maximum capacity is only 2 electrons. Well, the second and third box and so on, like 8 electrons so far. So far, the thing that you need to know, I think should be to this part. So let's say that we have 11 electrons. It means that the first box we have 2, and the second box we have 8, and the third box we have 1. So 2, 8, 1 would be the arrangement of electrons inside the boxes for sodium. If it is 17, then we have 2, 8, and 7. So it means that these things, sodium has 3 shells, because we need 3 boxes to fit all the electrons in sodium. So we have 3 boxes. In a periodic table, we can actually deduce the location of sodium by the number of shells. So the number of shells will also be the period. It means that this will be in period 3 because we need 3 boxes. Box 1, box 2, and box 3. So period 3, it means that periodic table is something like this. Okay. So 1, 2, and 3, it will be something like this. Yeah, so the third row from the top is the period. They're actually compiling atoms with the same number of shells, the period. So the row. So now let's compare sodium with another atom. Let's say lithium. Lithium actually 3 and 7 means that it has 3 electrons, 3 protons, 3 electrons. So if we would like to put the boxes, the electrons in lithium in boxes, we would make it like 2 and then 1. We see that lithium and sodium somehow shared the same last electron. And this is what we call bivalence electron. It's like the last electron on the shell. So they're actually showing us like in what group they are. So what group is the vertical thingy? So the row. Since they both have one valence electron, means they will be located on the same group. So on the first column. So based on the valence electron and the shells, we can actually predict the location of each atom in the periodic table. So if you have the row and you have the column, then you can actually know the exact position. Atoms within the same group, meaning that they have the same valence electron, will have similar characteristics, especially chemical characteristics. While atoms on the same period, so atoms that have the same number of shells will have the same number of shells. They're located in the same period. So these are all about atoms. So now I would like to discuss about pure and impure substances. So of course substances can be mixed. So for example like water, and then it's mixed with something else like alcohol, for example. We know that for water, the boiling point is actually 100 degrees Celsius and the freezing point is 0 degrees Celsius. Meaning that if we heat water, so let's say that this is ice, so this is temperature in degrees Celsius and this is time. So if we heat ice, let's say negative 10 degrees Celsius, at 0 degrees Celsius, the ice starts to melt. So it will start to melt until all of the ice is becoming water. Then, only then it can increase the temperature until it reaches 100 degrees Celsius. Then the water will also change form, change state of matter. They're using the energy to break the intermolecular forces. They're using the energy to change state of matter. So initially from water, they're transforming until all become water vapor. Then only then the temperature will increase. So you see that there are some instances where the graph is actually declining or increasing when we change the temperature. So we increase the temperature, the graph is, it has a gradient. So ice, the temperature is increasing. Then it has a horizontal phase. It has a phase where actually the temperature does not increase. Why? Because the energy is being used to change form or to break the intermolecular forces. The energy is actually being used. So there is no apparent temperature change here. But if we see, so if we cool things, yeah, it kind of happen like similarly. So we have, let's say, 110 degrees Celsius, then we cool it, becomes 100 degrees Celsius, then from vapor becomes water, then we cool, something like this. Yeah, so similar thing. We have a phase where it's actually horizontal. So here everything is water still. So it's changing. Here everything is gas. So in between, yeah, it's kind of mixed. So some parts already gas, some parts still water. But if you see from these two graphs, so this thing, so liquid is cooling. So let's say that this is a certain liquid that has like 45 degrees Celsius as the melting point. Let's say, yeah. So it's something, yeah, it's not water, I think. So here we see that this is a pure substance. So this is pure. Why do we know it's pure? Because all of the things are freezing together here. So all of the energy is being lost. They are forming intermolecular forces. They are forming solids. But if your thing is impure, so it's like a mix of different things, you see that initially it cools. And then now it shows that here it's freezing. But the freezing part, it's not horizontal. We still see change of temperature. What does it mean? It means that some part is freezing. Some part is actually making the IMF. While some part, yeah, I'm still not freezing, so I still want to reduce my temperature. Because it's like not all of the things are the same. So imagine like if we increase the temperature, the same thing will happen. So if it is pure substance, then something like this will happen. But if it is not pure substance, then maybe something like this will happen. So something like this, this. Yeah, so it's not really horizontal straight. Because here, let's say that this is solid. It wants to become liquid here. So from solid, it wants to become liquid. So like some part, they're not even using the energy to become liquid yet. So they still want to take the energy to increase the temperature. I hope it's clear that for the pure things, yeah, you see a very common pattern that they have a state where they just use the energy to change state. But in impure things, some of them are using it like that, but some, that's not their melting point, that's not their freezing point. So they still want to increase or decrease the temperature. So this is how we can see whether a thing is impure or pure. For example, like you're selling a precious thing, a precious liquid thing. This is also a way that you can do in order to make sure that the thing that you have is pure. Okay, so now let's speak about separation. Separation of particles, separation techniques. So we have multiple. One of the most common separation technique is actually called chromatography. Chroma means color. So here we're actually using something. So this is the solvent, and this is actually a thin paper. You see that actually this solvent will slowly move, right? So yeah, I think that's the behavior of solution of a liquid on thin paper. I think you would learn this in physics, capillary and other things. So since the solution moves, so the solvent moves, the solvent would also carry the things in the ink here, in the ink. While the solvent moves, the ink would also move, right? The ink would also carry pigments. And the pigments have different solubility, they have different mass as well. So of course, eventually, while the solvent would eventually reach this point, so the solvent, the water would move to this far, the lighter pigments would also move far, but not as far as the solvent, right? But you see here that there are some pigments that are kind of slow. Well, maybe because they are kind of heavy. In this case, just from this one ink, and by using chromatography, we're able to separate the pigments that are inside this ink. So here, every specific ink, every specific pigment will have its own retention factor. So this is, there is a formula for this. So the distance traveled by solute, so the distance traveled by this ink, divided by the distance traveled by the solvent. Yeah, so for example, let's say the solvent, so initially this is, let's say 0 centimeter, then this is 20 centimeter, let's say. The solvent front, so the solvent reaches to 20 centimeter. But the yellow thing, let's say that it reaches 18 centimeter. So the retention factor for the yellow ink would be 18 divided by 20, or around 0.9. While for the blue thing, let's say that it only reaches 9 centimeter. So the retention factor for the blue thing only 9 divided by 20, so 0.45. So different retention factors means that we can actually differentiate pigments or molecules. The lighter the pigment is, the further it will move. Does it mean that something is good if it has higher retention factor? It does not mean like that. It just means that your pigment, your molecule moves further. It has good solubility in that solvent and it can move further. So this is just a way to separate. So if you want to separate two things, well, we have to make sure that the retention factors actually different. So this is one way, by using a solvent and letting it move. Another way to separate things, we can also use a simple filtration technique. Just typical filtration technique. So let's say that here we have things that are easily separated, a mixture. So here when we pour the content of this beaker glass in a filter paper, for example, through a funnel, then the funnel will actually pass the water. So the liquid will actually pass through. So one of the things will be easier to pass through, because the objective of filtration, of course, to separate that one thing from the other, right? So of course we have to consider that one thing can pass through the filter and the other thing cannot pass. So the other thing that we want to separate will be contained on the filter paper. So the thing that is remaining in the filter paper will be called residue, while the thing that passed through the filter paper we will call filtrate. So usually we can use this method, for example, if one of the thing is actually solid or it's a precipitate. So just an example, you have a water and you have a sand. So a mixture between water and sand, we will be able to separate the water and the sand using a simple filtration method. Another way to separate things also, we can use evaporation method. So for example, something like this as well, water and sand, or maybe water and salt. We can actually boil them, yeah, using evaporating basin. So evaporating basin. So let's say that you have a liquid here and you use heat, and then of course the heat, you continue the heat until most of the water is gone and the remaining thing will be the things that you want to separate. So evaporation is also one method to separate things. So far we've learned 3 methods to separate mixture. So the first one is chromatography, based on the retention factor, based on the solubility, and based on the molecular weight. And the second method is of course to use filtration if one of the thing is actually solid or precipitate. So one of the thing can pass through the filter paper and the other cannot. And the third method is also kind of simple, evaporation. After evaporation, we can use crystallization. We can do crystallization. So for example, like this. Here we have a solid and we have a solvent. And then let's say that the solid can be dissolved. But this is still impure. And we want the pure crystals actually, yeah. But this thing can be dissolved. So we also use evaporation, so evaporating basin here. We use heat in order to remove most of the solvent, so most of the water usually. After some time, so most of the water will be gone, then we allow the solution to cool so that we will get these crystals. So these crystals would be pure, so no longer impure, but will be pure crystals. Then we can scoop these crystals and then we press it between filter paper so that the excess moisture will be gone. Then we get pure crystals. So crystallization is a part, crystallization. It's the important part of evaporation. The next separation method is actually called distillation. So distillation, actually it has two types. So the first one is simple distillation, the one that you see here in the picture below, and then what we call fractional distillation. Fractional distillation. Okay, so the concept of distillation is actually separation of liquid with something else. For simple distillation, usually we are separating liquid and let's say soluble solid. So within the liquid, within the solution, actually there are some soluble solids and we want to separate both of them. For example, we have water here and then the water actually contains some salt. Well, you know that salt solution is actually soluble, right? So it's kind of difficult for us to separate salt which is already dissolved into water. So even though you filter it using the finest coffee filter or whatever, I don't think that you can separate the salt crystals and the solution itself. So one of the methods to separate salt water so that you can have pure water and also salt is distillation, especially simple distillation. So how would we do that? Actually, we put the salt solution here, salt water for example, in the distillation flask. And then we use heat. Now let's say that the boiling point of the solvent, so the boiling point of the solvent is the temperature that usually we're going to use because we're going to evaporate the solvent. While the salt itself, I don't think like in these temperatures the salt would be able to evaporate, right? Meaning that after we evaporate the water, the salt will remain in the flask. So then let's say that the boiling point of water is 100 degrees Celsius, means that we can use something like 105 degrees Celsius, 110 degrees Celsius. Then the water would actually be turned into water vapor. Then what's the purpose of the thermometer here? Actually just to check if the boiling point has been achieved. So the water is actually going here, the water vapor. And the salt remains here. It will be pure salt actually. So it will be sticking on the wall of the flask. So the water vapor will actually journey through this funnel, this tunnel. And then it's still kind of hot. And you know that water vapor actually is gas. And gas, like the particles, they are white and they move very quickly. But then if we lower the temperature, then actually the particles will be closer to each other. The particles will lose energy, so the gas will turn back into liquid. Here. So here, actually, we have a system called condenser where we put cold water in. And then the cold water, it's not actually mixing, it's just like passing through. So like it's just a blanket. So blanketing the pipe, you can imagine like that. The goal is just to lower the temperature so that the water vapor will actually be colder. So here, the hot water vapor will be colder and colder and colder. So the particles will be closer, closer and closer, so that the gas particles will turn into pure liquid. And here we will have the distillate or pure water. So what remains in the original distillation flask will be only the salt, meaning that we have achieved separating the liquid and the soluble solid. And finally, we have fractional distillation. So in this case, sometimes we have a thing that is composed of many different things. So let's say that we have crude oil. So crude oil is actually containing a lot of fractions. So it contains a lot of fractions. From tiny fractions to big fractions, but they're combined in one big crude oil. So like there are tiny fractions here in crude oil, then there are also big fractions, and then also some moderate fractions, something like this. But also like very tiny fraction. So crude oil is actually a mix, a very random mix of these things. So imagine that if we hit this thing, if we hit it, then the thing with the lowest boiling point, well, if the boiling point is low, it means that we only need very small amount of heat, low temperature, and it's already boiling. It's already becoming vapor. So the smallest thing and the ones that have the lowest boiling point will actually move to the top of the fractional distillation. So this is called fractional distillation. And we use a big chamber here. So the one with the lowest boiling point will actually move to the top of the chamber, and then they will be expelled. So let's say that initially we hit this around 30 degrees Celsius. So the things that boil around that temperature can be separated, then we collect them. And then let's say now we increase the temperature to be 100 degrees Celsius. Then now the things that boil below that temperature will be moved, and then we can separate them also. And then we increase the temperature to 200 degrees Celsius, and so on and so forth. So fractional distillation actually also separate multiple things based on the difference of boiling temperature, boiling point. So we increase the temperature steadily to separate all of the fractions. And finally, usually for crude oil, the last fraction, so the one that has the highest boiling point, we use it as lubricating oil, paraffin, or asphalt. Asphalt for your roads. So these are all things that are important for you for MYP chemistry in the chapter of understanding matter. I hope this video helps, and I will provide also worksheets and some examples, practice questions in other videos. So thank you.